Okay, folks, I'm hoping that you're enjoying your spring break. I hope you're relaxing, not doing very much. I've recorded this video here, hopefully not to interrupt the good vibes here, but so that we can uh, so that we can finish up chapter 3 and hit some of the highlights that we haven't talked about before, and also just to get us ready for the next week when we're all back. Okay, and so I want to start here with a quick recap on changing bases with Dirac notation. So that is one of the powers of the Dirac notation, is that we can accomplish that base change fairly quickly, easily, and in a straightforward manner. We can also write things completely independent of any kind of basis. I remember back when we talked about the analogy to Euclidean vectors, right? So you can just draw the vector. It has a certain length and it has a certain direction, and you don't really need a coordinate system to describe that vector, but you can if you want to. You can describe the vector relative to a particular coordinate system, in which case then you specify the various components of the vector, basically the various projections of that vector onto your axes. So same thing here, we said with this Dirac notation, the bracket is sort of the bracket is sort of an inner product. It's a dot product, and that inner product is completely independent of any kind of basis, but you can also analyze it within a particular basis. Okay, same with the dot product, right? If you have two vectors, you dot them together, you don't really need components to evaluate the dot product. You can just say magnitude, length of the first vector, times length of the second vector, times the angle, cosine of the angle between them. But if you have a coordinate system in place, then you can also say a sub x, b sub x plus a sub y, b sub a, b sub y, and so on. All right, so let's delve in, shall we? We talked a little bit about this projection operator, p hat, alpha ket, alpha bra, okay, written in this particular order. So it's not an inner product, we call it an outer product. And an outer product is an operator, and an example of that would be spin 1/2. The nice thing about spin 1/2 systems is that they're two-dimensional, right? You have spin up and spin down, and those are the only two possible states along a particular axis. So it is certainly two-dimensional, and we only need two vectors, two kets to span that space. Why don't we use plus z and minus z, right? And we call that spin up, and this one spin down. But then any other vector, any other, state, spin state can be written as a superposition of these two because we have completeness, right? So for instance, I can write the plus x spin state. So this would be a spin pointing in the positive x direction. I can write that state as a superposition of plus z and minus z. And it's sort of an even superposition, right? An evenly weighted linear combination. All right, so let's look at that projection operator. I can project onto the plus z axis, or I can project onto the minus z axis, if you will. I should say state here in this case. So if we project onto the plus z state, then we're going to call that projection operator p plus, and similarly for p minus. Okay, so let's let the p plus act on this state plus x. So we want to project this state, spin state plus x, onto the plus z state. All right, and we get this nice inner product of plus z plus x. There we can very easily evaluate that because that is simply just the square root of 2. If you don't believe me, you can come up here and put a plus z on the left. Sort of come in here with a plus z bra. This goes away and you're really just picking out this particular number there. Okay, and so we have that, and so now I can do the same thing with the minus Okay, projection operator P minus, okay, same formula, and we get 1 over the square root of 2 times the minus z state. And then I can add them. Well, okay, here just to remind you here, where did these factors here, these prefactors of 1 over the square root of 2 come from? They are the coefficients multiplying the basis states here in my linear combination, right? So this one here is that, and this one here is that. So I'm picking out those coefficients. And so we see here that if I added those two lines together, the previous two lines, what would I get? Well, first I could actually also just factor out the plus x from both terms. But what I get when I add these two together is basically nothing other than the original state. Okay, so take a look at what happened here. If I add my two projection operators together and then let some arbitrary state here, in this case plus x, operate, let them operate on this arbitrary state, then I get that state back. Okay, and so we can say that the sum of those two projection operators does nothing to the state and therefore multiplies by 1. We can call the sum here just the unit operator. So this is an example of the formula we saw, the more general formula, that when I add all the projection operators associated with all the basis vectors, when I add them all together, I end up with 1. So in the two-dimensional space, of course, in this sum, there's only 2 terms. In a three-dimensional space, like say spin 1, there would be 3 terms in this sum, and they would have to add to 1. But we see that it is really just a statement of completeness, right? Any state can be reconstructed, as we just did, from the individual projections onto all the basis vectors. Okay, and this is then also true. This idea is true and generalizes to infinite dimensions. So when I have, say, a position space, I can say that this here is equal to 1 for a similar reason, because the position basis is complete again. I want to actually illustrate that here as well. So if I have here this inner product of psi with itself and it's a normalized state, then it has to be 1. We know this, and this is actually a statement that's independent of basis. We haven't yet injected any kind of coordinate system kind of basis into this description, but if we wanted to, I could evaluate this inner product in the position basis, in which case I would have to sort of wedge in this red integral into the inner product. As we said before, this is sort of more recap now, and as a second step, then I bring the bra and the ket inside of the integral, and I get these nice inner products inside the integral. And we recognize these inner products as simply just psi star and psi, and so I get an integral of psi star of x times psi of x over all of space, and we know that that has to be 1, okay, from way before. This is sort of how we started out the course. We know that has to be 1, and so it works also in this position basis, right? So we knew this already, that the inner product had to be 1, but if you sort of express this inner product in the position basis, we arrive at an expression that we already knew had to be 1. Okay, so let's go back to finite dimensional spaces, such as spin 1/2 or spin 1, 2-level systems. You name it. You basically want to have a system that has only a finite number of states available. So the system only has a finite number of states available to it. It can only exist in say, 1 of 2 states or 1 of 3 states, or in some linear combination of a finite number of states. Okay, and when that's the case, then we can represent the ket by a column vector. Okay, and so this arrow here is meant to symbolize represent. So this alpha ket can be represented by an n-dimensional column vector. Okay, so in this case of spin 1/2, that n-dimensional is just 2-dimensional column vector. And then I'm going to claim here for a moment that the corresponding bra must be represented by a row vector where the entries are also complex conjugated. The question is why? Why is the bra represented by a column vector? Well, because we know what we need to get from the inner product, right? We knew already that we need to get this answer out for the inner product. B1 star A1 plus B2 star A2 plus, and so on, up to B sub n star A sub n. So we know this is the answer, and we can kind of see now that this matrix multiplication between the row vector and the column vector gives us exactly this answer that we needed. Okay, and so what we can say that is if beta is represented by a column vector with entries B1, B2 all the way down to Bn, then the corresponding beta bra vector is then represented by a row vector where the entries are all starred, complex conjugated. Okay, and so that is sort of the rule. Here I'm using equal signs now because I guess for a purist it should be an arrow represented by, but oftentimes in quantum mechanics we'll just use the equal sign here. So then the question is, how do operators get represented? If the bras and the kets are column and row vectors respectively, then what is an operator? What does it look like in this representation? Well, we know that from before that an operator acting on a ket gives you another ket. So in our translated language now, something operating on a row vector should give you another row vector. In other words, you want to transform one column vector, I should say, one column vector, because we're talking about kets here, one column vector into another column vector. Okay, I need a function that takes you from column vector to column vector. Well, that is nothing other than a matrix. T must be represented by a matrix. Okay, and so if the column vector is n-dimensional, then this matrix has to be n by n, an n by n matrix. So here we go. We have T represented then by this matrix. Okay, and then if we apply this matrix to the column vector, in this case, we can really talk about multiplication. We multiply this matrix to the column vector, we get another column vector. Okay, and so the simplest possible basis spanning such a space is just what you wanted to do anyway. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Okay, so that's the easiest orthonormal basis, is if the first basis vector is just 1 followed by n minus 1 zeros, okay, and then the second one shifts the 1 down by 1, the third one shifts it down by 2, and the nth one shifts the 1 all the way to the n. Okay, and so then the question is, what is this kind of object in this representation of column vectors and this basis? Okay, so I come in with the ith of these in its bra form, and then over here is the jth eigenvector, a basis vector, I should say, the jth basis vector in here. And I multiply the matrix by the matrix from before by the jth basis vector, and then finally the result gets multiplied on the left here by the ith row vector. And you can convince yourself then that just picks out the T sub I j from before. Right, so in this matrix, it will pick out one particular element corresponding to the ith position, okay, and the ith horizontal position, the jth vertical position. Okay, so that is what we get here. So let's look at an important example to wrap this up. Okay, let's look at an important example. I want to sort of go down to two dimensions because it's just the easiest. Okay, so again, we are sort of in two-dimensional space. And here maybe we can have in mind a two-level system, or the object can be in two states. So maybe the ground state and the first excited state, and then all the other states are either too high or don't exist. Okay, so we're looking at the system being able to, at a certain temperature, being able to only occupy the ground state and the first excited state, two-level system. And so we are in two dimensions. And then, of course, the Hamiltonian is an operator, and all operators are n by n matrices. And here, therefore, it would take the form of a 2 by 2 matrix. So a common Hamiltonian that you encounter quite a bit in quantum mechanics is the following, where you have HG, GH. So H on the diagonal entries, and then G on the off-diagonal entries. Then we also know about the time-independent Schrödinger equation. Okay, and it looks like this. Now in our new representation, okay, in this representation of column vectors, we can write that equation in the following form, right? We have the Hamiltonian now, a 2 by 2 matrix, the state itself, an arbitrary state for now, but an eigenstate of energy, okay? An eigenstate of energy being represented by a two-dimensional column vector. And then here, E is just a scalar. And here's the column vector again. So what we see here is this is the classic eigenvalue problem. You know, this is what you start out with in linear algebra when you get to eigenvectors and eigenvalues. What you realize there is if you bring this right-hand side over to the left and then combine the scalar with the matrix, then you get basically this matrix here times the column vector has to be equal to 0. Right? So you bring this right-hand side over to the left, absorb the E into the matrix. It then appears on the diagonal, right, as a minus E. Okay, and that matrix multiplied by the column vector has to then be equal to 0 because you've shifted the right-hand side to the left. Well, if you don't want to get only the trivial solution where psi1 and psi2 here are 0, which is not a physical state anyway, if you want to get some other non-trivial solutions, then you better demand that this matrix out front here is non-invertible, because if it were invertible, I could invert it, and then I'd just get the trivial solution. So we need to demand that the determinant of that matrix here is 0. And so that is our characteristic equation, right? That will give us the eigenvalues and the eigenvectors. So just to demonstrate and to remind you how that's done, let's determine that determinant, right? The determinant is just H minus E times H minus E, that's the diagonal, and then minus the off diagonal multiplied together. G squared is equal to 0. And so I can solve that pretty easily. I get that H minus E is equal to plus or minus G, and therefore that E is equal to H plus minus G. I get two states. One is H minus G, and the other one is H plus G. So those are my two eigenvalues here, my two eigenvalues. That's usually how this whole thing goes. You find the eigenvalues first, and then you go back and find the corresponding eigenvectors, and that's what we're going to do next. What are the corresponding eigenvectors? Well, you basically, now that you have one of these eigenvalues, you just plug it into the characteristic equation again, right? You have then this, this is no longer an E here. This is now one of the eigenvalues, E1, H minus G, and you try to solve this for psi1 and psi2, right? And that would be the corresponding, once you have these entries here, psi1, psi2, that is our corresponding eigenvector. And so let's see what we get here. The first line gives us H times psi1 plus G times psi2 is equal to H minus G times psi1. The second line, similarly, And here, if you look at the first line, you know, h times psi1 is on the left here, but h times psi1 is also on the right. That will cancel out, and I get g times psi2 is equal to minus g times psi1. And then if I cancel the g's, I really am just going to get psi has to be minus psi1 has to be minus psi2. They have opposite signs. And so we get basically 1 minus 1, but it has to be normalized. The state has to be normalized, and therefore I get the prefactor being 1 over the square root of 2. So that is now my first eigenstate. Okay, here it is, 1 minus 1, and it goes along with the eigenvalue E1 h minus g. And then we have a second one that we can do in a similar way. We can get that out very, very similarly. Okay, and we would get 1, 1 with the normalization, same normalization constant out front. Okay, so we get these two eigenvectors with these two eigenvalues. Okay, so what does it all mean? Well, first, before we answer that, also notice that the two eigenvectors are indeed orthogonal to one another, and they're also probably normalized. So we can say that this would also be a suitable basis, an orthonormal basis, okay, using psi1 and psi2 state here. These two states, we could use that as another basis for our two-dimensional vector space. All right, so what does it all mean physically? So to answer that, we can first ask, what if the Hamiltonian had basically just had the diagonal entries and none of the off-diagonal entries? So what would have happened if G were 0? Then you can very quickly convince yourself then that these two states, 1, 0, and 0, 1, would have been perfectly good eigenstates. Right? They're both actually eigenstates. So if you multiply h hat to 1, 0, so that matrix up here to this column vector, what would you get? You get that column vector back times an h out front, right? H times this column vector. So the eigenvalue would have been h. If you apply this matrix to this column vector, okay, multiply them together, you would get this back with an h out front as well. So we can say that they both will have, these both would have an eigenvalue of h. So we have some degeneracy here. But once you introduce the cross terms, the g's here on the off diagonal, then these are no longer correct eigenstates. Okay, so sort of going down further in our sort of physical interpretation of what it all means, let's look at a double well. So here's my potential energy. It has one well here, and then there's a barrier here, and then there's another well here. Okay, and so maybe that barrier is very, very high. And so if you put a particle in this well, it doesn't really, since this is such a high barrier, it's not able to tunnel into this other well. Let's just say, okay, I've made this barrier very, very high, and I can't easily tunnel through. And so then we could say we have two possible states, one where the particle is trapped on the left and one where it's trapped on the right. That's our two-dimensional vector space, and the basis vectors that correspond to that would be 1, 0, and 0, 1. We said that those are eigenstates of the Hamiltonian, so basically energy eigenstates, only if there are no off-diagonal elements when the G is equal to 0, right? So let's lower that barrier just a little bit. And now there is tunneling, and so now I get this is now the eigenstate, the energy eigenstate. In this basis, using this as sort of our basis here, we could say that this state here has a little bit here and a little bit here, and they add constructively. That would be sort of this state plus that state, namely a 1, 1. Okay, and that's a symmetric state. But we also know that there exists an anti-symmetric state like that. And that would be the other energy eigenstate, where I take this state and then subtract that state. that state from it. I get a minus 1. Okay, so these then become the true energy eigenstates, as we just showed by finding the eigenvectors of that Hamiltonian that has the off diagonal entries, G. Okay, so these are then the correct eigenstates when there is sort of leakage from one well to another. We can say that that leakage, that tunneling from between, the tunneling through the barrier from one well to another, sort of is somehow related to the off diagonal element G. If I have a G, then I have that tunneling. If I don't have a G, then the barrier is so high that I don't get the tunneling. Okay. We can say that as the barrier in the middle increases in height, then that G here, that off diagonal element, gets smaller and smaller, and in the limit will just approach 0. In that case, then, when it does approach 0, the two eigenvalues actually both converge to H, right? Because one eigenvalue was H minus G, the other one was H plus G. If G goes to 0, they're basically both converging on H. And so then we have a degeneracy, because we have two states with the same eigenvalue, right? The same energy. We call that degeneracy. And now I can actually form linear combinations of the previous eigenstates, energy eigenstates, and that will still be an energy eigenstate. So if we have a degeneracy, I can form these linear combinations, and these linear combinations in that case of degeneracy, only there do I then get another energy eigenstate. So we can say that 1, 0 does actually become a suitable energy eigenstate, but only when you have this degeneracy, and only when that barrier in the middle goes to infinity, such that the off diagonal element G goes to 0. Okay, so these become then 1, 0, 0, and become acceptable energy eigenstates. So when the barrier in the middle is infinitely large, yeah, I can put an electron in the left well, and it will stay in the left well. So it is a stationary state, and therefore it is an energy eigenstate. And I can put it initially in the right well, and it will stay there, and it is a suitable energy eigenstate, a stationary state. But as soon as I lower that barrier, that is no longer true, and I have to form these even and odd linear combinations. All right, folks, enjoy the rest of your break, and I'll see you back here on Tuesday.